Great. Test. Can you hear me okay in the back? Good. Thank you. Hi, my name is Paco. I'm from O'Reilly Media. I've been working with the ÖSpark project for a while here. I was formerly at Databricks. And here to present about GraphX in particular, graph analytics in ÖSpark. Very grateful to be at Scala Days and have this opportunity. First off, how many folks have worked with ÖSpark before? Okay, a lot. That's great. Just a brief introduction here. I'm not going to go into a lot of detail about ÖSpark. There's some other great presentations if you want to get more of a deeper dive into the introduction, the fundamentals of ÖSpark. I know that Dean Wampler, Helena Edelson, also Andy Petrella, and others will be doing other ÖSpark talks as well. I'd like to pick up, though, at this point. When you take a look at ÖSpark, there is the core, there is the notion of working with RDDs, the base abstraction of having immutable distributed collections in Scala, being able to apply functions to those collections of data, those data sets out on a cluster. And so ÖSpark really came from the batch world. ÖSpark was intended to be a generation beyond Hadoop. If you take a look at the origins of Hadoop and MapReduce coming out of Google, circa 2003, really, when the work was being done, a lot of the problems that they were facing were the difficulties, the risks of running large-scale machine learning workloads on a cluster with commodity hardware. And at the time, of course, in 2003, the big problem was spinny disks failing. If you run a cluster of 2,000 nodes for a full day, you have an expected value, even today, of having at least 10 nodes failing. And so having to restart jobs because nodes were failing, because disks were crashing, that was a problem that Google struggled with. They came up with GFS, the distributed file system, and they came up with MapReduce as a fault-tolerant way to run the compute on top of that. But that was 2003, and looking almost a decade later, ÖSpark came out. It went open source in 2010, and really the objective there is, by virtue of what's available in Scala, we have much better software for being able to handle distributed systems, much better formalisms, and as well the hardware that's called commodity hardware had changed over a decade. So, you know, when you look at the difference between, say, circa 2003 and circa 2010, there's huge advances in terms of multi-core, large memory spaces, SSDs, et cetera, et cetera. So ÖSpark is largely about being able to take advantage of a new generation of software, a new generation of hardware, and be able to get a lot better throughput, a lot better pipelining on clusters. And so the ÖSpark core really took off, but also a lot of the benefit of having ÖSpark was that you could leverage the abstractions in it, the RDDs, to be able to provide other types of use cases on top. So if you think about SQL, if you think about manipulating tables and having a notion of schema and doing joins and all, there's a nice correspondence between the base abstraction in ÖSpark, the RDDs, and a relational table. So we can do ÖSpark SQL, where effectively we register the RDDs, or now the data frames. We register those with an internal catalog, and then we can use them in the from clauses of SQL queries. And then the result sets that come back from a SQL query are likewise this same abstraction, a data frame. So building on top of ÖSpark core, you can get ÖSpark SQL. If you take a look at microbatch, where you have a time window from about a half second up, any data that comes in on receivers during that particular time window becomes an RDD, and then the rest of the processing downstream is effectively the same kind of functional programming you'd be doing with ÖSpark and batch. If you look at machine learning with MLlib, you think about the training vectors that you have to prepare to be able to create some kind of model, and the test vectors that you use for evaluation. These are also RDDs and now data frames. And so the abstractions fit very well. But fourthly, there is this newer component called GraphX. I'll go into it in more detail, but it's a way of leveraging the same abstraction, RDDs and now data frames on top, to be able to build out a large distributed graph and apply functional programming to do your graph algorithms. And the big thing that I want to stress with this perspective here, this landscape, is that a lot of times when you're building up applications, you do have the component of needing to do your ETL, needing to do all your data preparation, put together your training vectors, do your holdouts for your test vectors, et cetera, et cetera. You need to build up pipelines. You need to build workflows. And there are a number of different types of graph packages at scale, and there's some excellent packages out there. But what Spark is really focusing on is the problem that we want to build apps in Scala that incorporate these different parts. How can we build a combined workflow that integrates ETL with some machine learning and some graph algorithms? So I'm going to focus on the GraphX part of it, but that's a lot of the rhyme and reason of how we got here. I've got a number of slides here. I probably won't go into huge detail in terms of time, but they'll be in the slide set if you want to take a look. The main thing that distinguishes Spark from Hadoop, the generation before, was that it does provide for what we call lazy evaluation. You write your program, and the program is on the client side, and you're working with the REPL on the client side, but then when you actually need to get a piece of data, some kind of result out, then this whole DAG of your application, this whole directed acyclic graph that describes your application is serialized out to the cluster, run on the cluster, and results come back. So we have this notion of lazy evaluation of big data apps, and it provides a mechanism for being able to do fault tolerance, for doing parallelism, and for doing lots of interesting optimizations. And that allows us to be able to get away from having so many synchronization barriers that we would have had previously in Hadoop, and for a much better pipelining effect on clusters as a result. Now, proof is in the pudding about Spark. If you haven't seen, there was a world record set last November by the Spark team. Previously, it had been held by Yahoo. They had used about a 2,000 node cluster running Hadoop to do a 100 terabyte sort for the Gray Sort Challenge. And the Spark team came back and did the same thing 3 times faster with a cluster that was 1/10 the size, about 200 nodes. And looking at the metrics across the board, it is about a 30x improvement. The other difference is that Yahoo never really published what type of hardware they were using. It was on a dedicated data center. But the new world record, there were 3 PRs. It's all public. And a lot of that is going back into Spark proper. It was done on Amazon AWS. So if you want to replicate the results, that's all open. I will also point out that there was an O'Reilly survey that shows that people working with Spark get higher median salaries. So if you want to take that back to your bosses, it's a good value prop. And also there was a great survey by TypeSafe showing for people who are working with big data what types of tools, what types of languages and process they're using. I highly recommend that. Okay, so that's a little background on Spark. But let's drill down on the graph algorithms part. GraphX, the graph part of Spark, really comes from 2 parents. There was work done on GraphLab, coming out of, I believe, CMU. And Joseph Gonzalez was one of the authors of GraphLab. He was a postdoc at Berkeley and put that API on top of Spark. There was also work implementing the Pregel paper out of Google on top of Spark, a project called Bagel. And so these 2 came together into what's now known as GraphX. The key point is that looking at GraphLab, reading the original paper from GraphLab, they define the notion of graph parallel systems, a category of processing that if the problem satisfies its constraints, then we can do very interesting work in parallel on commodity hardware. And again, the real thing that we're stressing is the emphasis on integrated workflows. Spark does a number of different types of things, streaming, SQL, et cetera. But really, the value prop is pulling these together into combined apps. Here's a few links if you want some of the background. The first one is the original GraphLab paper. The second one is some of the Pregel research out of Google, and a couple of recent talks from the Spark committers working very closely with GraphX. But the big notion is this. If I can take and define the data for all of the nodes, all of the vertices in a graph, and then parallelize that collection. I come up with an RDD describing the nodes in the graph. And each node is going to have a unique identifier, which needs to be a long, and then some other type, some other data affiliated with that node. So that's some arbitrary type ND. And then if I take and have another collection of the edges, the connections between the nodes in the graph, then similarly I'll parallelize them and create an RDD of edges. And there's a built-in type called edge, but it expects a certain type for the attribute data, some piece of information on the edge connecting two nodes. So I'll take these two RDDs and compose them together into a graph. And now the type signature on the graph is that I've got the node data type and the edge attribute well-defined. And then from that graph, G, I can apply functions to it, and I'll get RDDs out as the result set. So there's a very nice tie-in between the functional programming that we would do with RDDs in Spark in general and how we can do our graph analytics. So as an example program, I know this is a little bit harder to read here. I've got a notebook to show it. But the idea is I've got some people, and for each person there's a unique identifier. There's a node in the graph. And there's also some other information. There's a case class that gives the name and the age of the person. And then the edges connecting these people, there's some attribute. It's a strength of a connection, let's say, some sort of social network, if you will. We take and create a node RDD, an edge RDD, compose them into a graph, and then down at the bottom, it's doing a very simple traversal across the triples, the connections, and just filtering out for the strongest connections. This is a very trivial algorithm, but it does show the basics of how to work with GraphX. Going into something more interesting, though, if you take a look at a graph like this, I've got 4 nodes and then some edges connecting them, and I've got some costs as the attributes on the edges. You could think of this as maybe being 4 different metro airports and the time it takes to fly between them. This is a very common problem in industry. When you look at what FedEx does, when you look at what, I don't know, United Airlines does, when you look at routing problems in general, or supply chain, or maintenance schedules, this is a common problem for optimization throughout industry. A lot of large operations research kinds of problems. And this is very convenient to do as a graph data structure, a graph algorithm. Dijkstra's algorithm, of course, is a very classic way to do this, and there are some great ways to implement that in Scala, in Spark. So let's check that out a bit. I've got here a notebook. How many folks are using notebooks of some flavor? IPython, Spark Notebook, Zeppelin, those kind of things? Okay, great. I'm a big fan of it. Jupyter is the new project beyond IPython, and there is a Scala backend for it. So here we've got a Scala notebook running on Databricks Cloud. It's containerized, running on EC2. And basically, the idea of a notebook is I've got a lot of different cells. They could be markdown, such as this one right here, or they could be a code cell, something to be interpreted, or they could be output, basically the results from running the code. And you can take and move these cells around if you need to, but basically there's some data flow between them. And it's a very convenient way of having a number of people work together. Essentially, it looks a lot like a Google spreadsheet. It's a shared document that runs in a browser, but it has the server, the cluster on the back end. So here I've got that first GraphX program that I showed before. A bunch of people, their names and ages, and then strings of connections between them, compose them into a graph. You can see the results there. And then I can run just some very simple filter across that. And it sees, you get the results there. Pat loves Kim. If I want to do something more complex, though, here's an implementation of Dijkstra. It's a single source shortest path, or you might argue it's actually single destination shortest path. But SSSP implemented in GraphX using the Pregel abstraction. So I've got here some of the data that was in the previous slide, basically this diagram. And I create a node RDD, an edge RDD, compose them into a graph. And then I'll come up with a shadow graph, if you will, mirroring that. One of the nodes is tied down as the goal. This is what we're trying to route back to, node 0. And then the costs on each of the edges is initialized to positive infinity, worst case cost. And then from there, we start to run Dijkstra on that. Here's a very succinct implementation of SSSP in Scala. Basically, we're sending messages around until we get the optimal results, and then we print those out. So down here, results for the routes in that map. It's trivial to go from node 0 to node 0. It was 0 cost. But it's more interesting, say, to go from node 3 to node 0, where it's a cost of 2, and here's the routes that you have to take. That's the kind of thing, like I say, FedEx does this all day, every day. Now, I'd like to present real briefly about graph analytics, go into a little more detail there. A lot of real-world problems we see where the data can be represented as graphs. And generally, you can represent graphs as some type of sparse matrix. You can do transition matrices, depending on how you're going to manipulate the graph. There's a few different flavors of these. Once you've got your data as a matrix, then we can start to apply a lot of interesting linear algebra to be able to do parallel processing on it. For instance, we don't necessarily have to use graph packages. Twitter, for instance, has an excellent project called AlgeBird, and inside of that there's the Matrix API, and they do a lot of their revenue apps using the linear algebra approaches. Basically, you can find the eigenvalues and eigenvectors of a system and then use that to get some of your graph metrics up. And also, interestingly, if you go beyond that, if you look at more complex graphs, then you start to move beyond working with matrices. Instead, you're typically starting to work with tensors. So a general case of working with a lot of real-world problems would be where they're represented as tensors and you do some kind of tensor factorization. And I think that's interesting because it's on the horizon. It's definitely starting to show up. So here, we've got a graph. We've got 4 nodes, 4 vertices, and the edges between them. We can take and transform that into a matrix and then do some linear algebra on it. And, oh, by the way, if you really do like sparse matrices, I'd highly recommend there's a museum of these. Each has a MATLAB code fragment to visualize them. It's kind of fun. These are actually very useful for doing test cases for different machine learning algorithms. But the one note about graph algorithms looking out on the horizon, what I'd like to point to is that more of a general case would be to do tensor factorization, and there's some very interesting work in this based on Spark. Anima Anandkumar at UC Irvine is doing work, and I think that this would have a huge impact on big data workflows in industry in general. For one thing, it could really cut down the amount of code that we have to write to handle a lot of these interesting data scenarios. David Gleich at Purdue is another one who's doing similar work. Okay, so there's a project called Exto, and the goal of the project is to be able to point to any email developer community email forum for Apache. In this case, we used Apache Spark, but equally we could point out to any other Apache project. It's got a scraper, it's got a parser, it does a little bit of natural language processing, uses WordNet, and produces JSON documents to represent the email conversations. From there, in Spark, we build up graphs to represent the senders and repliers, et cetera, in the developer community, and then be able to take a look at who are the leaders, who are the people who are interested in particular topics, who are the people who are most engaged, helping out new users of Spark. But beyond that, also being able to use graph analytics to do some text analysis, being able to do topic modeling in a fairly unique kind of way based off of GraphX. So this is all available on GitHub. I'm going to show it in notebooks, but I've taken the notebook source and exported it and checked it into the GitHub repo. Okay, so an interesting thing here is that if you look at the developer community in Spark, if you look at the email forums, it's not a whole lot of data. It's about 2,000 messages per month, and represented as JSON, that's about 18 megs per month. It's not big. It represents about 2,000 senders, approximately, so far, at least for the past 6 months. And I can build a social graph of that that's about 2 million nodes and about 3 million edges. So even though it's not a lot of source data in JSON, once you start to represent it as a graph, it gets much larger. And then if you start to look at the semantic relations within the text and build up graphs to represent that, the NLP processing, of course, you can get huge graphs. And that's the interesting part. Basically, at that point, the data explodes. But it is a graph parallel system, or it can satisfy that definition. So we can leverage data locality and get a lot of benefit by using GraphX. Just real briefly, here's some view of the pipelines, the workloads involved. We've got some work on the parsing and all to get the data. But then once we have it, we'll do a little bit of the exploration, surface some leaderboards, do some queries, and then do some featurization and more community insights downstream. I'll move through this. Basically, a lot of JSON. I'm not going to go into too much detail on that. So the code for this in a notebook is right here. First off, we'll bring in, I've got some Python. I was using NLTK because of the WordNet bindings. I haven't done a good Scala implementation of this yet, but we're working on that. But I wanted to leverage some out of text blob and NLTK to be able to do a light parsing over the top. And basically, at the end of the day, I'm going to cut through this here, but at the end of the day, we're going to come up with representations of our JSON, drop them into Parquet data sets. They start out being JSON documents in an S3 bucket, but they end up being large distributed data sets in Parquet. And Parquet is the best practice that we recommend when you're working with Spark. You get the benefit of having the distributed storage, but as well, it's a column store orientation, so you can get some very nice compression then per column. And as well, it keeps track of the metadata. So it's a nice way to basically snapshot your workflow at a point in time. But moreover, it allows for push-down predicates. So we can have a large Spark application, but then we can actually move predicates around because of lazy evaluation and push them into Parquet. So for instance, if you have a data set that has 100 columns wide, but you have a query that only needs 3 of those columns, you can push that down, do a filter scan, and only deserialize the columns that you need. You can get some great efficiencies out of that. So long and short of this is I create Parquet data sets by doing some ETL, and then I come in here and I've got a Scala notebook that will read the Parquet. I've got the edge data, the node data. In this case, they're coming in as data frames directly from Parquet. And from there, I can compose a graph. Now, I'm just going to show one message, just in the interest of computing this and visualizing it. I'm going to show one message being analyzed, but we can do all of the messages in parallel, do them all simultaneously. There's actually some benefits to that. So here I've got a message ID out of one of the exchanges in the past 6 months, and I'll bring in my imports for GraphX. I can do some SQL. In this case, I could do SQL programmatically by just specifying the SQL as a string. Use that to do a little bit of filtering on the data. But here I build up my node RDD, and then likewise, I build up the edge RDD and compose them into a graph. And once I've got the graph, then I can start to do some interesting algorithms on them. There's a few different flavors of PageRank that are built into Spark. In this case, there's one in GraphX that's built on top of Pregel. And Pregel is a very nice abstraction. It's really only about 5 lines of code to implement implement PageRank in Pregel. And so it's just one line of code to say my graph G run PageRank with a particular convergence factor there. And then I pull the vertices out. Those will be the ranks. So what I'm going to do here is a trick with natural language processing. What happens is we're using something called text rank, and I can show this back here in the slides. It's probably a little bit better. I'm using an algorithm that leverages PageRank and leverages a light view of parsing the text, leveraging some of the semantic relationships, to be able to create a graph out of any arbitrary piece of text and do automatic document summarization. So there's this algorithm that comes from Radha Mahasya. She did the work at University of Northern Texas in 2004, 2005, went to Google for a while, and now she's at UMichigan. And the idea is this. If we have a piece of text, we can take the paragraphs, split them into sentences. So we've got a collection of sentences. And then for each sentence, we'll segment it into words. So we've got a collection of words. And for each word, we'll go and do a little bit of statistical parsing, tagging, if you will, and some lemmatization, basically looking up the roots of words. So if I have a noun that's plural, I can find the singular form as its canonical representation. If I have a verb, I can find its infinitive as a canonical representation. So I end up getting a tuple for each word. And then I'll take and run a skipgram over that. It's with a window of 3, I'll take a look at any of the verbs, nouns, or adjectives that are within the window and create links between them. But if there are words that have common roots, I'll also create other links between those. So from some arbitrary piece of text, I can generate a graph. And now the interesting thing is that when you go and run PageRank on this graph and basically pull the thread from the most highly ranked noun phrases, you end up with automated summarizations. So if you've ever seen scientific papers where, you know, in the right-hand column, the editors have gone in and written some summarization of the document, this actually competes with it pretty well. It's a great way of being able to put together featurization if you're going to build a custom search engine. We used this on a project I was on, building a custom search engine for Rolling Stone for some of their back catalog of magazine articles. And so an illustration here would be if I have this sentence, compatibility of linear systems, systems of linear constraints, then I end up with a data structure here in JSON to represent that sentence, and then I can build a graph by doing the skipgram analysis. Okay, and then I run PageRank. So the code for that, back here, I've run PageRank here, and we'll take a look at the results basically by doing a query on them. For a given email message that I was analyzing, it comes out with ranks, memory, persist, etc., the higher ranked nouns. That's interesting, but what I really want are to get the noun phrases. So I'll take these and aggregate them with their neighbors, and then take the aggregate PageRank for those noun phrases to be able to find out which are the most interesting descriptions of the text. So here, let's see, we've got the summarization. I'll actually show you what the raw data looks like. One thing that's interesting with ＳPARC is that when you read in JSON, the actual raw JSON data, it automatically generates the schema over the top of that. So for instance, I pulled in the JSON from the parse, and I do print schema, and it'll show you actually the nested data, which is a very nice convenience. So down here, let me scroll down here a bit. I've got a little bit of Scala. I've got a function that will take the ranked words and then aggregate them into noun phrases. And then from there, we'll run a query on the results. And so here you can see, after doing this processing, I come out with this description of the email message. It says that memory crunch was the most important phrase, followed by MapReduce operations, iterative algorithm, etc. Now, if you take a look at what the raw data had, you can see this is a pretty good match. It was talking about iterative algorithms, talking about MapReduce operations, better not to have a cache if you have a memory crunch, etc., etc. So you get a much richer representation of a fragment of text than you would if you were just doing keyword analysis. And at the end of the day, that's the goal. How can we have really rich feature vectors to describe our data? If you did take a look at just the keyword view of this, if I pull out the keywords, it's not nearly as interesting. So this is great if you're building up search, especially. Okay, so that's one view of using graph algorithms in this kind of developer community analysis. Another view, though, would be to take a look at the social graph. And this area of graph algorithms, of course, has been popularized by social media, Facebook, Twitter, etc. So here, I'll take and create a graph of the people who are the senders of email messages and the people who reply. And so, we create a graph, and also we're using PageRank. We'll get the vertices out and then take a look at them. And as well, we'll get some metrics on the graph. What are the in degrees? What's the maximum in degree? What's the maximum out degree? And basically taking a look at the shape of the graph. And then from there, at the bottom, we've got another algorithm we'll use called strongly connected components, basically seeing are there cliques of people talking together on particular topics. And so when I run the results on that, it's very interesting. My friend Sean Owen, who's head of data science at Cloudera in London, turns out that he's the most highly ranked contributor in the Apache community, at least over the past 6-month period. And indeed, when you look at a time series perspective of this, Sean is there like all day, every day. So it does work out pretty well, these metrics. Akhil Das from Sigmoid is also very heavily engaged, et cetera, et cetera. But this is a nice way to start to use the raw text from email and do some graph algorithms and then come out with who are the people who are engaged and what are they talking about, what are the topics. And it's also interesting when you look at the company affiliations, how are particular companies responding to other companies across an open source email list, and what are the topics that they're talking about. Another thing I should add, when you look at the shape of this graph, it's interesting, as far as connected components, it doesn't really give much information. Really, there's one large component and a few other tiny, small ones. And what that says is that the committers, the people who are really active in the Spark community, are there on the email list like every day. And they're very much engaged with a wide range of people. So they provide a backbone for the graph and tightly intertwine it. So there's not a lot of little orphan cliques within this community. Actually, at the end of the day, everybody's pretty much talking with everybody else. So if you want to see the code for that, it's pretty much what I'd shown before. I've actually got another, sorry. Yeah, here's the social graph. Okay, let's see, what time are we at? 58. Now, where we're going with this is to provide a kind of tooling to analyze developer communities through their email forums, but then also bring in additional linked data, do more graph analysis by taking a look at what's coming off of Meetup, for instance. Being able to enrich the data that we have off the email forums by where are some of the more active committers, where are they going off and doing conference talks or Meetup talks, and get additional signals on them from there. One thing that's come out recently was I saw a paper or an article by Matt Cruz, basically taking and using the ranked phrases like we produce with TextRank. They'd be nice features to run into, say, Word2Vec, and then from there doing clustering on Word2Vec as an alternative form of doing topic modeling. In text analytics, there's an algorithm that's very general purpose called LDA, latent Dirichlet allocation. It's very general purpose, but it is sensitive to noise. I've used it in large-scale chat systems, and the chat data is very dirty. It's not very good text. There's a lot of slang that's being used, for instance. So LDA gets confused, but this approach looks like it has a little bit more legs to it for the long term. Also, just one thing I want to point to, in terms of the Spark community, on the slides I'll have a few different resources I wanted to point out. One is there's a Spark developer certification. It's being done between Databricks and O'Reilly, and it's 40 multiple choice questions. If you have any questions about developer cert, I helped put together the exam, so I'd be happy to answer questions about that. Another thing is, as far as the community for Spark is concerned, the best resource is exactly these email lists that I was pointing to. user@spark.apache.org and dev@spark.apache.org. The committers are there on a daily basis, and they really prefer that as the main channel to have discussions about the code. There's also a directory structure, sorry, an event directory that shows Spark-related talks worldwide. We're trying to catalog those and do some data mining on it. There's a YouTube channel for Apache Spark. We try to do live streaming from meetups and then archive the videos. And of course, there's a couple of MOOCs that have just come out. Anthony Joseph just started one the 1st of June, and then Meet Talwalker, who had done MLlib as his PhD. He's starting up at the end of June, scalable machine learning in Spark. And another thing I want to point to is that we will be having Spark Summit here in Amsterdam beginning on October 27th. There's a call for papers that's out currently, and registrations will open up on June 15th. And if you talk to me afterwards, I've got some discount codes if you want to go to Spark Summit Europe. Alrighty, and a few books and videos if you want to learn more about Spark. If you want to get a hold of me, I've got my contacts on LinkedIn and newsletter and things like that. All right. Thank you very much. I'd love to take some questions. I appreciate it. Any questions? Yes? Well, you know, so one thing I didn't put in here, but I have the links, I can bring it up. So to repeat the question, there are other graph systems. One that I really like, I've done some work with, done some training for, is called Titan. And it works by basically having a denormalized graph. You denormalize per node information about the edges that are in the neighborhood, and then you denormalize per edge the information about the neighbors, the nodes that are in the neighborhood, and that way you can get a lot better throughput on the cluster. And so this works on top of Cassandra, it works on top of Accumulo, HBase, et cetera. And the team was recently acquired by DataStax. And so great folks. There's also a very nicely layered API, Tinkerpop, and recently there's integration between Tinkerpop and Spark. But the thing is they drill down directly to RDDs. They're not using GraphX. So that remains to be seen, but there have been definitely discussions between the two teams about how to integrate more closely. At the end of the day, a lot of the problems that we see doing graph algorithms at scale, a lot of the costs are more on the ETL side. You know, data preparation, DJ Patil talks about data science, the data prep is 80% of the problem, 80% of the cost perpetually. And we do see that when you're doing large-scale graph work, say with Giraffe, ETL costs can really kill you. So one nice thing with Spark is just trying to have these integrated workflows where ETL is a first-class citizen. So not a lot of tight integration yet with projects like Titan, but I think down the road there could be. Yeah.
So just preparing a very large graph, like the way you're doing nodes versus the edges.
Yeah.
It's really a small part of the problem itself.
Well, it's interesting. Not exactly. So it does depend on what type of application you have. We know of large-scale use cases with GraphX and streaming. For instance, where you've got some stream that's coming in and updating the information on the graph, and then you only take a look at the deltas. You really take a subgraph of what's changed and run the algorithms on those. So in that case, actually preparing the nodes and edges really is a big cost factor because it's always being updated and you want to get, you know, effectively real-time analytics. So, other questions? Okay, well, we can go to break and I can answer some questions afterwards there. Thank you very much. Have a great Scholar Days.